So the topic for today is rounding LPs, and sort of in parentheses I'll say randomized. So this is a very important topic in combinatorial optimization, or in general sort of discrete optimization, is for many problems, we write an integer program and relax to an LP, but the resulting polytope, which comes from the LP, is not integral. So in the previous lecture, we saw a number of cases where actually, somewhat magically, the resulting polytope is integral. This is for like cuts and flows and for bipartite matching. And then we discovered that there was this notion of total unimodularity, which sort of was an underpinning theory to why these LPs were actually integral. But for many problems, the matrix is not totally unimodular, and we don't get an LP. We don't get an integral polytope. And the question is, how can we use LPs to solve such problems? And so for this lecture, specifically, I'm going to consider a class of what are called covering problems, because this is a very good vehicle to explain the concept of rounding. So let's start with a classic problem, and this is vertex cover. So vertex cover is you're given a graph, a simple graph, G of V comma E. Find the smallest subset. Find smallest subset, A smallest subset, S subset equal to V, such that every edge has at least one endpoint in S. Right, so what you want to do is, here's your graph. This is S. What you want is for all the edges to have at least one endpoint. They may have both. This should not happen. There should not be an edge such that both endpoints lie outside of S. Okay, this is the vertex cover problem, or technically the min vertex cover problem. And so we can write an LP for this, and the LP actually is fairly easy to write. So we sum over all vertices of xv, and we have a constraint that for all edges, xu plus xv has to be at least 1, and of course we have a non-negativity constraint. Now in the IP, we would have said xv has to be in 0, 1. So the IP would have had an integral constraint on xv, and if you have xv being either 0 or 1, then this integer program is exactly vertex cover, because what this is saying is for any edge, the sum of those variables has to be more than 1, which means one of them has to be at least 1. Now, on the other hand, when in the relaxation, we just keep a non-negativity constraint. Is there any questions about this? So this is the LP here. Okay, and this LP is not integral. It is only integral if the graph is bipartite. Or rather, I should say, if the graph is bipartite, then the LP is integral. That's the correct way to say this. So here's an exercise. If G is bipartite, then the LP is integral. But if G is not bipartite, LP is only a relaxation. So what does relaxation mean? Relaxation means that all feasible points of the IP are feasible in the LP, but LP may have non-integral vertices. So another way that this is interpreted is that the solution to the LP is a fractional vertex cover. What this means is you can imagine that XV is like a fraction. It's like saying that instead of in the IP, either you take a point or you don't take a point. A vertex, I'm sorry. Either you take a vertex, which is 0, or you don't. I'm sorry. Either you take a vertex, which means XV is 1, or you don't take a vertex, XV is 0. In the LP, you get to fractionally pick a vertex. So think of XV is like the fraction of the vertex you're picking. And as another exercise that I will state here, you can argue that in an optimal solution, XV is actually going to be less than or equal to 1. So one can argue that. You don't even need to put that constraint explicitly. Because if you think about it, if XV is strictly greater than 1, then you can always reduce it and maintain feasibility. So XV is like a fraction. XV is something in 0 and 1, and it's like taking a fraction of a vertex. And so rounding is a scheme or an algorithm that converts fractional solutions into integral solutions. So the general scheme for this is you write an IP, you relax the IP to an LP, solve the LP, you get a fractional point, and then you have a rounding scheme that converts the fractional point into an integral point. And there are sort of very common methods to do this, and one is called randomized rounding, which is a very powerful technique, and it's used to prove it's in a whole host of results. And what we will see over this lecture and the next lecture are a number of instances of randomized rounding, very beautiful applications of randomized rounding for a number of optimization problems. Now, before I talk about vertex covers specifically, I want to give you the schema, the overall proof schema of a rounding mechanism. So here's how it typically will work. The analysis of rounding will usually follow the scheme. So starting with any feasible, and this is sort of feasible again in the LP, feasible point X, rounding converts to a feasible IP point, which I'll call X integral. Now, let us consider minimization problems. Minimization problems such as vertex cover. And for convenience, let cost of x denote the objective value of x. Right? So for any point, cost of x will just denote the objective. Now what happens is when you round it, the cost will go up. The cost may potentially go up. Rounding potentially increases the cost. So we try to bound, and this is what happens in the analysis. We try to bound cost of xi should be at most alpha times cost of x, and so alpha is something greater than 1. So we try to get an upper bound saying that, well, the cost of the integral point is going to be at most alpha times the cost of the fractional point. So we prove something like this. I should say, instead of we try to bound, I will just say, like, so we prove a bound of this form. This is in the analysis. So we get some alpha over here. And then I'm just going to write out the entire schema, although typically in the proof one doesn't write the following details. Then you say, okay, suppose let x star be the opt of the LP. Right? This is the optimal point of the LP, or maybe I should say be the optimizer of the LP with cost opt LP, right? So that's the optimum cost of the LP. So what you then say is, okay, so the cost of xi star, which is the rounding of the optimal point. So let's say you take the optimal point, you round it. This is obviously more, at least the opt of the IP, just because this is an integral point. This is an integral point. And this, as we argue from here, is alpha times the cost of x star, but that's just alpha times the cost, and this is equal to alpha times opt of the LP, but note that this is at most alpha times the opt of the IP, and this is because LP is a relaxation. Right? The LP may have points that are not present in the IP, but the LP has all the points of the IP. And so when you string it all together, what you get, when you put everything together, you get the cost of xi star is at most alpha times opt of the IP and at least opt of the IP. And this yields an alpha approximation algorithm. It's a very, very important concept. This is an alpha approximation algorithm that is achieved by rounding. So what the schema says, you basically apply rounding on any point, and there's an alpha increase in the cost when you do the rounding. There's at most an alpha increase in the cost. So the cost will go up, but it goes at most by an alpha factor. And if you can prove this bound of alpha, then this logic over here gives you an alpha approximation algorithm. So typically when you see an analysis and proof, it won't have any of this part over here. None of this is going to be present. It'll just give a bound of the rounding, upper bound. Okay? Any questions?
Where is the randomized part here?
So the randomness is typically in the rounding. The rounding will be potentially randomized. Now I'll talk about this. So this procedure that converts a feasible LP point to an IP point will use randomization. Any other questions?
the polytope for the IP is usually, it has to be smaller than the polytope for the LP, right?
Yes, yes.
So how exactly would randomization work?
I will show you. You'll see some examples of that. I will show you that. Okay, so this is an alpha approximation algorithm. There is one more important definition that I want to give before we actually talk about randomization, which is we can ask, what are the limits of such an approach? Note that in this approach, we have a specific LP that we have defined. Now, consider the ratio, the opt of the, so let's see if I write this properly, right? This is a minimization problem. So if you consider the opt of the IP divided by the opt of the LP. So note that this is always going to be greater than 1 because the LP is a relaxation. So the LP might actually have a smaller cost. But this ratio is called the integrality gap. This ratio is a lower bound on alpha because it says that if you start with the optimal LP point, when you do a rounding, it will go up by, the cost will go up by at least the integrality gap. Okay, so I'll say this again. So the integrality gap, so when we do any rounding, the cost of x I star is at least the integrality gap times the cost of x. Right? Simply because the lowest possible cost of x star I is the cost of the IP, and the cost of the LP, the opt of the LP, is a lower bound on the cost of x. So the cost of x I star is at least going to be the opt of the IP. So when you do any rounding, you get this bound. Hence, the integrality gap is a lower bound on the approximation ratio or factor. The ideal rounding scheme achieves alpha equal to the integrality gap. The integrality gap depends on the specific LP. You could come up with different LPs for the same IP, right? You could fix the IP, but you could come up with different relaxations in the hope of reducing the integrality gap. By the way, all of this was discussed with respect to minimization. For maximization, you need to flip things, and you'll get the integrality gap being less than 1 as opposed to more than 1. So in maximization problems, all of these are flipped. I'm not going to write everything down, and it sort of flips in the natural way. But these are two. So I've sort of mentioned 3 very important concepts here. The notion of rounding, the notion of approximation algorithms, and the notion of the integrality gap. Any questions about these? Any questions, please? So sort of very important concepts in approximation algorithms or in general combinatorial algorithms. And the notion of the integrality gap. So you'll see multiple papers actually, will prove integrality gaps, or they will try to prove that if your rounding scheme does not achieve the integrality gap, then you have to either improve your rounding scheme or potentially prove another integrality, like improve the integrality gap, like prove a larger integrality gap. So this will come from typically hard instances. So I'll give you examples of these so that it will become more concrete. But any questions so far? All right. Okay, so I want to go back now to, let's go back to vertex cover. And let me give you a very simple rounding scheme so that, we can understand all of these concepts in a very simple way. So here the rounding scheme is very easy. The rounding scheme for vertex cover. Simply take the set to be all v such that xv is greater than equal to half. This is the rounding scheme. So you can think of one way of rounding is simply say that xi is just going to be 1 if xi of, I'm sorry, this is a bit overloaded notation here. So xi of the vertex v, right, subscript v, if xy is greater than equal to half or 0 otherwise. This is the rounding scheme, but we can just think of it as taking this set. Okay, so why is this a cover? Why is S a cover? Looking at the LP, can someone tell me why the set is a cover? Will it be a cover if I replace the half by 2/3?
No.
No. So why is this a cover?
So I'm guessing that this is happening because we have to argue that u and v both cannot be less than half simultaneously.
Right. And why is that the case?
But I don't see why.
Look at the constraints of the LP.
So the key is that this is a vertex cover, not.
Oh, yeah, xu plus xv is for all edges xu plus xv is greater than equal to 1. So PHP will tell you at least 1 has to be greater than half.
Why even PHP, right? Just average.
Just average, yeah.
Just average. But sorry, so someone else was saying something.
The key is that this is a vertex cover and not a minimum vertex cover.
But no, you have to prove that this is a vertex cover. How do you prove that this set is a vertex cover? You're right that this may not be a min vertex. How do you prove that this is a vertex cover? And this is provably a vertex cover because of this constraint. When xu plus xv is greater than equal to 1 for every edge, obviously one of those has to be at least a half. And therefore, for every edge, one of the endpoints is in your set. Right? S is a vertex cover because for all uv in E, xu plus xv is greater than 1. So 1 of xu xv is greater than a half. So S is a vertex cover. Okay. Now how do you, what is this alpha? So I said that when you do this rounding, the cost is potentially going to go up. Can you guess what this alpha factor is going to be? By how much is the cost going to go up?
The size of E, or N, where N is the number of vertices.
Well, it will, but N is a large, extremely large. I mean, that would, so the problem is an N approximation of vertex cover is trivial. Just take all the vertices, and that's an N approximation.
So it'll go up by, at most, N over 2, right? If all of the vertices are set to 1/2.
If all of the vertices were set to 1/2 and you did the rounding scheme, what is alpha? Alpha is actually much smaller. Alpha is smaller. So yeah, you're thinking about, good. So you're thinking about the right way of looking at this is, again, let's go back to what alpha is, right? So you want to say, what is the cost of xi divided by the cost of x? So what is the cost of xi? Right? The cost of xi is just the size of the set. Right? Because that's the, you're rounding everything to binary. And so the cost of xi is just the size of the set. What is the cost of x? That's just the sum of xv of v and v. Can you give me an upper bound on that? So let me give you a simple upper bound. Actually, before I do that, so any further thoughts? Like, what kind of bound could you give for this?
Like, I think an obvious bound is 2.
Okay, why is 2 a bound?
At most, you'll have everything being propped up to 1, like.
Right.
But that's not tight, probably.
It is tight.
Oh.
It is tight. And I'll show you why it is tight. So you're absolutely right, because you're bumping everything up by at most a factor of 2, right? So what is the size of S? That's just, I can write this as, it's 1 for every vertex in S. And this, by the rounding scheme, is at most 2 times xv for all vertices in S. And this is at most 2 times the summation of xv for all vertices in V, which is 2 times the cost of x. Right? So this alpha factor over here that we got was 2. And this is a 2 approximation to vertex cover. Any questions about this, right? So I chose vertex cover because it's an extremely simple example, but it demonstrates this idea of rounding. This is the rounding scheme, and this is how you got a 2-factor. So for any, there were doubts about whether this is a 2-factor, please ask me questions and make sure that you understand why you got this 2-factor. Okay, now let me actually show that the integrality gap of the LP is at least 2 minus little o of 1. It's basically 2. So this is the best possible we could hope for. This is like the optimal for that LP. We can show this. And the integrality gap example is actually quite simple. So consider a clique of n vertices. What is the optimal value of the integer program? Clique on n vertices. What is the size of the vertex, min vertex cover? What is the size of the minimum vertex cover in a clique? What is the minimum vertex cover size of a clique?
1.
It's not 1. Vertex cover, right? You need to get vertices such that every edge has an endpoint in the set.
Ceiling of n by 2. Or is it n?
It's not ceiling of n over 2. Here's a graph. It's a clique. You need to pick vertices so that every edge has an endpoint in the set. If you only pick half the vertices, you could have an edge which sits outside that half, right? And it would not be a vertex cover. What's the minimum vertex cover of a clique? N minus 1, exactly. Right? Because if you leave any two vertices, then they're going to have an edge between them and it's not a vertex cover any longer. So the optimum is n minus 1. What is the opt of the LP? What is the opt of the LP? If you could put fractional, it's a clique, put fractional values there to satisfy these conditions and minimize, what would you do? Think about the rounding scheme. Think about what the rounding scheme was doing and try to imagine how could you take fractional vertices and minimize things. So obviously if you take integrals, if xu and xv had to be 1 or 0, then n minus 1 is the right answer. What if you could take fractions? What could you hope for?
N over 2.
Then you could put half.
N over 2, you put half everywhere. So the opt of the LP is, I mean in this case it's equal, but we can say that it's at most n over 2, right? So for all v, xv is equal to half. This is feasible. Hence the integrality gap, which is the opt of the IP divided by the opt of the LP, is at least n minus 1 divided by n over 2. And this is basically 2 minus little o of 1. We actually know that the integrality gap is at most 2. And that's because we've proven that it is at most 2. We know that when we round, we'll get at most a 2 factor. So the integrality gap is basically 2. And there is a 2 approximation to vertex cover. So this is the best possible with this specific program. We've done the best we can. It turns out, it is conjectured that you cannot beat this assuming P not equal to NP. Although that's not been proven yet, it is conjectured that there is no better approximation to min vertex cover assuming P not equal to NP. It has been proven assuming unique games, assuming something called the unique games conjecture. Has been proven assuming something called the unique games conjecture, which I don't want to get into. So it's actually conjectured that there is no better. So remarkably, this two-factor that we got is believed to be the best. Indeed, there's an even simpler two-approximation algorithm, which I'll put as an exercise. A very simple two-approximation that doesn't use LPs is to simply take the maximum, to take any maximal matching. Okay, so any questions? I hope this was one of the simplest examples I can show of an approximation algorithm using rounding and an integrality gap in this case, which is tight. Right? So this is called tight because essentially we have achieved the ideal rounding scheme for this LP. Maybe there's a better LP, but it is conjectured that there is no better LP. Indeed, it is conjectured that, forget LPs, that it is conjectured that there is no better, I should say, polynomial time approximation to min vertex cover. Of course, in exponential time, you can solve it exactly. But it's believed that in polynomial time, you cannot beat this. Okay, any questions?
So for the bipartite case, that follows from the matching, right?
Yes. For the bipartite case, exactly. It's Konig's theorem. I mean, there are multiple ways of seeing it, but I take that. It follows from matching. Basically, if you take the dual of the vertex cover LP that I wrote, then you essentially get a matching problem. And we know that for bipartite graphs, that matching problem is actually integral. And because the dual is integral, essentially all the optimum is integral, and that's how it holds. Yeah. So, or you could take the dual, which gives you a matching problem. Then by Konig's theorem, you know that the max matching is min vertex cover. Any other questions? Okay. And this is a big sort of open problem. That can you prove, assuming P not equal to NP, that there is no better approximation than 2? And the best people have shown there is no root 2 approximation to vertex cover. So, okay. So that was a simple example where we had an integrality gap and an approximation algorithm. And what now I want to do is a more sophisticated example following similar lines. This is again for cover, and this is a famous problem known as set cover. This is another sort of classic NP-hard problem. I should have mentioned that min vertex cover is NP-hard. So what is the problem of set cover? So we're given a family of sets S1, S2 up to Sm over a universe U, and we will assume that the union of the SIs is equal to U, right? So this is basically, think of it as you have some universe and you have a family of sets that covers this universe. A set cover is a subfamily Si1, Si2 up to Sik, such that the union of Sij, j going from 1 to k is U. So any collection of sets, any subfamily of sets whose union is the universe is a set cover. So find the size of the smallest set cover. Again, this is a classic NP-hard problem. Convenient representation convenient graph representation is given by what is called the set element incidence graph, or you can also think of it as a matrix. I like to think of this sort of graphical representation that on one side you have the sets. So let's just say there are m sets, right? So there's S1 to Sm, and over here you have the elements. And for convenience, I'm just going to say the universe goes from 1 to n. So I number 1 to n, and I put an edge for incidence. So if j is in Si, then ij is an edge. So in what I'm going to say over here, so sorry, ignore the j that I used over there. I will use I to index the sets. I will use j to index the elements. And you can see this representation essentially, it's nice because there's a symmetry between the sets and the elements. So what you want to do is in this graphical representation, you want to pick the minimum number of vertices. You want to pick the minimum number of vertices on the left, so these are sets, such that the union of neighborhoods, is everything. Right? You want to pick the minimum number of vertices so that the union of neighborhoods is everything. So let's write an LP, or let's write an IP which we will relax. So let's write an IP, then relax to an LP. So what we'll have is xi is a variable indicating whether we pick Si in our cover. Right, so the question is, are you going to pick this set or not? So we have a variable that indicates that. So what we want to do is we want to minimize the number of sets that we pick. But now what we want is the constraint that all the elements are covered. What is the constraint that I would write? So I want a constraint for all elements. I need to write some constraint. What is the constraint that I'm going to get? Think of it from this. I want to ensure that I have covered the element j. What is the constraint that I need to write? What is the constraint? Any suggestions?
We have to pick all of the vertices in the left half of the bipartite graph that have an edge to j.
You don't have to pick all of them. You just need to pick one of them, right? Because you just want the union of neighborhoods to be this. Right? So you need to pick vertices over here so that the union of the neighborhoods is everything. What this means is for this vertex, you want to pick at least one of these, one of its neighbors. Does that make sense? Remember, in the set cover, you just need to pick some set that contains that element. So what you get here is, it's the summation over all xi such that Si contains j, and this needs to be greater than 1. In the integral case, this would say, therefore, if this is greater than 1, there exists some set that you have picked that contains this. And so in the IP, we would enforce xi to be in 0, 1. But in the LP, we'll just say xi is greater than 0. We'll just leave it as a non-negative constraint. This is the LP here. Any questions about this LP? So I'll leave a simple exercise is that in the optimal LP solution, for all I, xi is going to be at most 1. So you don't even need to add this constraint that xi is going to be at most 1. And again, sort of if anything is more than 1, you can always reduce it and maintain feasibility. Okay, so now let me discuss a rounding scheme. And actually, this is going to be sort of a two-shot process. I'll discuss one rounding scheme, and that's not going to completely cut it. So we're going to have to update it. So I'll just do rounding scheme number 1. And this is going to be the randomized rounding. So we know that for all I, xi is in 0 and 1. So let us interpret it as a probability. So just interpret xi as a probability. This is a very common technique in randomized algorithm, in rounding, which is you interpret an xi, which is fractional. You just interpret the fraction as a probability. And so the rounding scheme is simply for each I, pick set Si with probability. So maybe I'll just expand this out. With probability Xi. Very simple. So we're just going to pick every set with probability Xi. Does the rounding scheme make sense? This is the randomized rounding here. So this is how we convert a fractional solution into an integral solution using randomization.
How do we get the guarantee that sum of xi is equal to 1?
Good. No. So we are actually not going to get that guarantee here. It's a good question. But we will get something, and then we'll use that to get the final rounding scheme. Yeah, you're right that we won't guarantee that. Instead, what I'm going to show you is that you get something. You get a cover that is sort of good enough. So I'll prove this claim that for each element j, the probability that j is covered is going to be at least 1 minus 1 over e. Okay, what is the proof of this? Okay, so what is the probability that j is not covered? And so let's go back to this sort of picture here. Here was j, and these are all the xi's. So you have every xi over here corresponding to each of, this is Si contains j, right? So when Si contains j, you have some xi. And so you picked xi1, xi2, so on and so forth. And so if any one of those was picked, then j would be covered. So for j to not be covered, I should say, sorry, pick set, I should say independently. Right? So you do an independent experiment for each of the SIs. So the probability that j is not covered is exactly the product of I such that Si contains j of 1 minus xi. Right? Because it means that you did not pick each of these sets. For each of these, you had a probability of xi. And so that is exactly what you get. And now using the expression 1 minus x is less than e to the minus x for, x having absolute value of 1, I'll just now say that this is at most e to the minus sum of xi, si containing j. What is this quantity? What is that numerator? That is at least 1 by the properties of the LP. That is at least 1 by the LP. And hence, this is at most e to the minus 1. And so we're done. That's a probability that j is not covered, so the probability j of covered is at least 1 minus that. Right? So work of art. So for every element, the probability that it is covered is at least 1 minus 1 over e. So you get constant probability of covering every element. Now we'll come up with the final rounding scheme. Is repeat rounding scheme number 1 independently for 2 log n times. Take the union, or take the subfamily of all sets chosen. And what I'm going to prove, so here is the theorem, is that with probability at least 1 minus 1 over n. So it's like with very high probability, the rounding scheme outputs a set cover. The expected, so in this case you don't get an approximation factor, you get an expected approximation factor, but that's good enough. The expected approximation factor is 2 log n. So another way of saying this is you get a 2 log n approximation for set cover. So let me prove this, and the proof now is pretty straightforward. You repeat it 2 log n times. The probability that, okay, so fix j, the probability that j is not covered after 2 log n iterations, and again these were independent iterations of scheme 1. So this probability is at most 1 over e to the power 2 log n, right? Because the probability that it was covered is at least 1 minus 1 over e. The probability that it is not covered is at most 1 over e. And this had to happen, it was not covered in all the 2 log n iterations. And so you get this, which is essentially 1 over n squared. By the union bound over all j, over all j. So this is the probability of the union of events over j, that j is not covered. Right? This probability is at most the sum over all j. The probability is j is not covered. And this is at most n times 1 over n squared, which is 1 over n. Right? And so that proves the first part. So with probability 1 minus 1 over n, all elements are covered. With probability at least 1 minus 1 over n, all elements are covered. The expected number of sets chosen in each iteration is exactly the sum over xi of right? It's basically because we pick every set with probability xi. So the expected number of sets we pick is linearity of expectation that I've used here. So the expected number of sets that we pick is the summation of xi. And this is exactly, this is basically just the cost of x. And we repeat 2 log n times. So we get 2 log n approximation in expectation. Okay, any questions? Any questions?
Not a question, but can you hold this note for like a couple of minutes?
Sure. I mean, I'm also going to scan it and send it to you, so good. But okay, so I hope, let me just sort of do a run through of the whole scheme. So I'm just going to put something in front and I'll take it away. We wrote the IP. Our first rounding scheme was to simply interpret every xi as a probability, and we pick every set with probability xi. So we pick si with probability xi. So as is correctly pointed out, this is not going to be a cover. On the other hand, we can prove that it's sort of, for every element, the probability that it is covered is at least 1 minus 1 over e, or the probability that it is not covered is at most 1 over e. So that gives us the final scheme. We say, okay, we'll just repeat the whole rounding scheme independently 2 log n times. 2 of the natural log n times. And we just take every set that has been chosen. And what we can guarantee is that with probability at least 1 minus 1 over n, the rounding scheme outputs a set cover. The expected approximation factor is 2 log n, because that's just the number of times. Each time when we pick, the expected number of sets we pick is exactly the cost of the point, right? So this gives the 2 log n approximation for set cover. Let me know when I can continue. In the meantime, I'll...
Sure.
Sorry?
Yeah, I'm good.
Okay. Any questions? Any questions? Okay, so that gives that proof. Now what I'll actually show you is a very interesting construction. The integrality gap is, we won't get exactly 2 log n. It turns out it's actually not. It's not 2 log n. It's going to be a little smaller than that, but we get it up to a constant. Is specifically what we'll get. We'll get log base 2 of n divided by 2. So we get that so actually our rounding scheme was pretty good, because up to constant factors, because the dominant term is a logarithmic term. The construction here is much more sophisticated, so please pay attention. It's a bit of a tricky construction. So we'll just let n be a power of 2. So it's 2 to the k. The universe consists of k-dimensional vectors over F2, the binary field. So it's basically, the universe is F2 to the k, and we'll take the non-zero vectors. Non-zero just means that you don't take the all zeros vector. Take everything else other than the non-zero vector. So this is simply saying that the universe, these are all k-bit binary strings with, arithmetic over the binary field. Okay, so the universe size is n minus 1 because we didn't take the zero vector. We took everything else. So f2 to the k minus 1. That's the universe size. Okay, so I've told you the universe. Now I need to tell you the sets. Now the sets are also going to be indexed by the elements. So for every vector a in f2 to the k, I'll say in the universe u, right? So this is the universe. So for every a in the universe, define the set S sub a to be as follows. It's the set of all vectors b such that a dot b is equal to 1. Where this is just the dot product operation over vectors, right? These are vectors over a field. If you want to think of it as binary, then it's basically just saying a dot b is equivalent to 1 mod 2. Let me just write. Sorry, any questions? All right. So here are the sets, but the sets are also indexed by the elements, right? So the sets in some sense are indexed, and here is the universe U. They're the same size, and what you get over here is, you can think of this being indexed by A and B, and this an edge. Edge means that the dot product is 1. That's what the edge means. So this is a regular bipartite graph. Regular bipartite. What is the degree in this graph? What is the degree in this graph? If you fix an A, how many B's can have this property? Any thoughts? Any guesses? What is the degree?
Are you not getting a degree in expectation? Is it like...
There's no randomness here, right? There is no this is a specific construction.
A is a string from like 0, 1, like is a binary string, k-bit binary string, right?
Right.
So A dot B equal to 1 will be for like true or false depending on the size of that set depends on the specific instance of A.
Does it? Is the question. I claim it doesn't. It's the same. It's a vector space. This is like an affine. This is an affine space.
Right.
So how many points? Let me keep it simple. Suppose A has one non-zero coordinate. That's it. So A has a single non-zero coordinate and that's it. Then what is the size?
One. Right.
Why would it be 1? So if A is a k-bit string, how many k-bit strings satisfy this property? Right, what is this? This is summation of AI, BI, I going from 1 to k. So think of it as a bunch of linear equations. This is a single linear equation over F2. Right? So maybe let me write this out separately. Let me write this out here, right? So fix AI, right? So if I take summation AI xi, I going from 1 to k, and this is equal to 1, how many solutions do I have for this equation? I'm making life even simple for you. A1 is equal to 1 and all other AIs are 0. How many solutions are there?
Is it 2 to the k minus 1?
2 to the k minus 1, exactly. So it's 2 to the k minus 1, and this is essentially n divided by 2. Right? It's basically, you're taking this vector space and you're taking one constraint. So every time you take one constraint, you get half the points. Indeed,
but how is this true for all instances of
take
AI?
a linear transformation and transform it into this. You can basically take a linear transformation and you can transform, up to a linear transformation, you can convert any A into this. Or you can look at it as what is the rank.
Oh yeah, we
can
just essentially we are changing the axes.
You're changing the axes, or another way to look at it is that look at the rank of this space.
Yeah.
Right. So basically, in some sense, the codimension is 1, so the dimension is k minus 1.
Yeah.
Right. You can also look at it in terms of essentially you can look at the rank of this. So the rank of this is 1. It's just one equation.
Hi, Sash.
Yeah.
You mean when you say the rank of the space, you mean the dimension?
The dimension, yeah. But the thing is that if you're looking at all the x's that satisfy this condition, they lie in a lower dimensional subspace. Everything sits in k dimensions, but that's all the points. When you put a linear constraint and you're looking at all the ones that satisfy that linear constraint, it's one dimensional lower. And when you reduce the dimension by 1, so you get 2 to the k minus 1 points. So the degree is n over 2. Okay, this is important because the degree is n over 2. Let me now give you a fractional cover. What is the fractional cover? Simply set for all a, set xa to be 2 divided by n, which is sort of essentially the reciprocal of the degree. Observe that for all b, the summation of xa such that ab is an edge is 1. Hence, this is a cover. The cost, or the objective, is just the summation of xa over all a in the universe. And what you get is you get n minus 1 times 2 over n. So you essentially get 2 minus little o of 1. So the fractional cover basically has size 2. But we will show that a set cover has size at least k, which is log base 2 of n. And so that gives the integrality gap of log base 2 of n divided by 2. Okay, so consider any a1, a2 up to ak minus 1. So look at any set of elements of that form. So there are multiple ways of looking at this, and I'll give you both. So it turns out that the rank of the linear span of a1, a2 up to ak minus 1, this is just k minus 1. The rank of the entire space, f2 to the k, is k. Hence, the null space of A1, A2 up to AK minus 1, the null space has dimension 1 and is non-empty. So there exists a B such that a non-zero B such that for all, I'll say such that A1 dot B is equal to A2 dot B is equal to AK minus 1 dot B is 0. So A1, so SA1, SA2 up to SAK minus 1 is not a cover. Because there is this element, non-zero element, that has not been covered. The only way it is covered is if it has a dot product of 1 with someone in this collection. But these are k minus 1 vectors, so they span a k minus 1 dimensional subspace. So therefore, the null space, you can look at the null space, or you can, another way of looking at this is consider this set of equations, just write out these equations. A1 dot x is equal to 0, A2 dot x is equal to 0, so on and so forth up to AK minus 1 dot x is equal to 0. This system of linear equations has rank k minus 1. The dimension of x is k. So there has to exist a non-zero solution for this system. That non-zero solution is a point in the space that is not covered. And so the integrality gap is basically at least log base 2 of n divided by 2 minus little o of 1. I just put over here minus a little o of 1. So the integrality gap is log base 2 of n divided by 2. So this is a clever construction, right? This is not as simple as that clique construction. Any questions? Any questions about this? Right? Now, having talked about set cover, there is no way that I can not tell you about the greedy algorithm for set cover. Maybe you've already seen it. But this is sort of as a side. So we've discussed the linear programming approach for set cover. We got a 2 log n approximation with an integrality gap of omega log n. Again, it turns out in this case, for set cover specifically, there's a simple algorithm that doesn't involve LPs that gives you a good approximation factor, and that is greedy for set cover. It's a very simple algorithm, so I'll just write it out explicitly. So we will construct a cover C. Okay, so initialize C to be the empty family. And say while C is not a cover, pick S that covers the most number of uncovered elements. I'll just write it mathematically. S maximizes S intersect whatever has not been covered so far. There's a union C, right? This is maximizing. So you can think of it as here's your universe. You picked a set that has covered this. Then you pick another set that's covered this. And then you pick another set. Of course, these might overlap. That covers this. So you look at the set that maximizes the number of uncovered elements, and then you pick that set. Now that might actually have some overlap, but you don't care. So this is just a very simple greedy algorithm, and you just add S to your cover. This is greedy. What greedy is? It's sort of the most obvious thing that you might, or a very natural algorithm that you might come up with. Any questions? The theorem is that, and this is what I will call the greedy algorithm, is an Hn approximation for set cover, and recall that Hn is the n harmonic number, so it's 1 divided by I going from 1 to n is the natural log of n. So greedy actually gives a log n approximation. So effectively the way to think of it is this is a natural log n approximation for set cover. Before I prove this theorem, I'll prove it. I will state that there is a very important result of phi k, I think it's probably O2, is that assuming P not equal to NP, there is no polynomial time 1 minus epsilon log n approximation for set cover. Right, so for all epsilon, right? For all epsilon greater than 0, assuming P is the best you can do. So this log n that we got here is, essentially, it's what we got in the round scheme. We got it with a factor 2. If you're a little bit more careful, you can try to improve on that. You can get closer to a natural log n approximation. We proved an integrality gap, which sort of gave us evidence that, maybe this log factor can't be beaten. And indeed, there's an alternate algorithm that gives log n, the greedy algorithm. And moreover, assuming P not equal to NP, you cannot improve on that. So, proving this theorem, this would require us to get into things like ECPs, which would be beyond the scope of this course. But my point is to tell you that it's a very important fact for you to, at least if nothing else, you remember that set cover has a log n approximation, natural log n approximation. This is given by the greedy algorithm. One can also get log n approximations with a slightly the worst constant factor using randomized rounding. The nice thing about randomized rounding, sort of like greedy, which is a generic approach, and randomized rounding also gives you a log n factor. Any questions? The proof of this, it's surprisingly clever and short, so I will like to show it to you. And this is something worth looking over. The proof. It's a very beautiful statement. So let me just prove that greedy is a log n approximation. So let's suppose greedy picked R sets. Okay, I'm going to introduce some notation. I'll say let Ni be equal to the number of uncovered elements after ith set is chosen. So I'll say N0 is just the original universe size n, and NR is going to be 0, which means that Ci be the number of new elements covered by the ith set. So the way to think of this is, let's say this is the situation before the ith set is chosen. So this has been covered, and the size of this is Ni minus 1. Then the next set is chosen. So maybe it's that. So these elements here, this is going to be Ci, and then all of this is going to be covered. So what we get is this simple relationship that Ni is equal to, this is Ni minus 1 minus Ci. I'm sorry, so I messed up, my apologies. I switch things over here. So let me draw this again. So here, this isn't covered so far. This is n-1. That's what's uncovered. Then a set comes in, covers that. So this part here is Ci, which will then get covered. And so Ni will decrease by Ci. Okay? Okay. Now let's look at the situation when the ith set is at the ith iteration, Ci is the largest possible number of uncovered elements in any set. Right? Because that's what greedy does. Greedy picked Ci, tried to maximize Ci by picking the largest possible number of uncovered elements in any set. Now, there is a cover of size opt, where we can just think of this as opt of the IP, which I'll just refer to as opt. Hence, there is a set covering Ni-1 divided by opt new elements. It's just saying that you look at the portion that's been uncovered, you know that before picking Ci there were Ni-1 things that were uncovered. There are opt sets that cover everything. So just by averaging Ni-1 divided by opt, there is a set that covers that many new elements. And so what you get divided by opt. Written alternately, this is just the same as saying, I'm just going to rearrange this and say this is opt times Ci divided by Ni-1. And now I'm going to do something clever here. I'm just going to write this as opt of 1 divided by Ni-1 plus 1 divided by Ni-1 minus 1 plus 1 divided by Ni-1 minus 2, so on and so forth. I do this Ci times, and I will get exactly at Ni plus 1 divided by Ni minus 1. So I'm just going to rewrite this over here. I'm just saying that I can rewrite this as saying 1 is at most opt times 1 divided by Ni-1 plus 1 divided by Ni-1 minus 1 plus 1 divided by Ni-1 minus 2, so on and so forth, 1 divided by n of I minus 1. Now let's sum over all R iterations, right? Because we said that greedy picked R sets. So I get R is at most opt times the summation. So now I have I going from 1 to R. All of what I have is here I have a summation. Yes, I'll just call this K going from Ni minus 1 to Ni minus 1 of 1 divided by K. So I go from Ni minus 1 to Ni minus 1, and the next iteration I go from Ni to Ni plus 1 minus 1, so on and so forth. So when I add this of 1 over K, which is exactly the harmonic number. And what that does is that proves that greedy is a log n approximation. Now, this is somewhat a tangent from the discussion of LP rounding algorithms. On the other hand, this is very much an important fact that if you've taken in the advanced algorithms course that you should know. Excuse me, that for cover, greedy is a log n approximation. The idea, it's a clever analysis. It basically says that if you look at greedy picked R sets, you keep track of how many uncovered elements there are after every set is chosen. So at some point, after picking I-1 sets, there are Ni-1 sets that are elements that are uncovered. Then Ci is what is covered by the newth set, the ith set. So Ni is equal to Ni-1 minus Ci, because Ci is what gets covered, and what's uncovered now is Ni. Now you chose Ci to maximize what was covered. And this is where you bring in op. You say, well, there's an optimal number of sets that covers everything. So the optimal number of sets covers all this uncovered portion, which means there is a set that's covering ni minus 1 divided by op. There is a set that covers that many elements. Greedy is going to do at least that. So Ci is at least ni minus 1 divided by op. After that, you basically do some clever manipulations and get the harmonic number. And what is maybe absolutely magical, if you think about it, is actually assuming P not equal to NP, you can't beat this.
Hi, Sash. I have a question, sir. I thought that we chose Ci to maximize the elements to cover, not was cover, right? Because every step you choose a new set, and then there are some new elements that to be covered, right?
Yeah, so the ones that are to be covered are the ones that are uncovered. Another way of thinking of this is think of everything initially is uncovered. And then you pick sets one by one to cover everything. You want to minimize the number of sets that you pick to cover. If you want to think of this graph over here, you can pick something with the highest degree, with the next highest degree. You pick that, then you throw all of its neighbors away because you've already covered them. And you proceed that manner. Does that make sense?
Yeah.
So this is what Ni, and so the key equation you get is that Ci is at least Ni minus 1 divided by opt. And after that, you basically do some manipulations to get the harmonic number. Okay, after that, you have to do some manipulations and do these, you do sort of these clever algebraic manipulations and you get the harmonic number out of this. Right, so you get 1 is most opt times Ci divided by N minus 1. So Ci times 1 over N minus 1, you write it as 1 over N minus 1 plus 1 over minus 1, so on and so on. This is upper bound. And there are exactly Ci terms here. So you use this equation to say, oh, I get 1 divided by Ni minus 1. And then you basically sum all of these things up over the iterations, over the R iterations. And so we get the R, which is the number of sets that you picked, is the most opt times the harmonic number, the nth harmonic number. And that's the analysis of set cover, the algorithm for set cover. Now, as I said, this is sort of tangent with respect to rounding LPs. But on the other hand, I just want to show you that for set cover, you have this LP approach, you have the greedy approach, and ignoring the constant, they both give you this log n approximation. And indeed, there was I was thinking of covering yet another version called max coverage, which also gives where you can also look at greedy and you could look at randomized rounding. But sort of stepping back, important parts that I would like you to learn from today's lecture, and please go and visit these concepts, are the notion of an approximation algorithm, the notion of rounding in LP, and the notion of an integrality gap. And use the vertex cover example to really understand these, because the vertex cover example is so simple. Once you really get that, then you can look at set cover. The greedy analysis is somewhat of a tangent from that. It's somewhat separate, although it is something that I'd like you to know. In next lecture, we will do randomized rounding schemes for cut problems, which is another very fascinating, it's almost an entire field of study. And this will give you even more sophisticated randomized rounding schemes, compared to the ones that we did today. So I'll end the lecture here and I'll take any questions that you have.
I have questions.
Yes.
I still didn't get why we need P doesn't equal to NP.
You mean for this theorem?
Yeah. Why we need that assumption?
Otherwise it's not, because if P was equal to NP, then set cover can be solved in polynomial time. The question is to try to see what you can do in polynomial time, but you need to assume P is not equal to NP for anything in that. If someone had proven this without assuming P not equal to NP, then they would have actually proven that P is not equal to NP.
Yeah, simple. I got it.
Yeah. Okay, any other questions? Okay then, so so Basu, you still can back out of the notes if you want at this point, but you need to let me know now.
No, it's okay. It's okay. I'll actually start writing now and see how far I get.
So yeah, write whatever you can, and you can leave. I will make a pass over the notes and polish them.
Yeah, I think the hardest problem here was the fractional, the field over 0, 1, the k-bit binary string thing, which I got like I realized much later what was going on. But everything else should be okay.
Yeah, everything else is yeah, I think so. I mean, even that, once you understand, once you look at the rank, then it sort of is fairly clear what's going on.
It should have been more obvious, but somehow I completely missed it.
Yeah, I mean, once you look at rank, it's sort of fairly obvious, right? You have a system of, it's all basically null space and because it's a field, it's f2 to the n, you can do linear transformations to transform anything to anything, right? So.
Yeah, I think this shouldn't be too hard. Like, it's quite a few pages now that I look at it. But
yeah, no, it is going to be at least 4 or 5 pages of notes. Like when you actually fill in all the details and you write everything.
I think it should be okay.
Yeah. I was actually hoping to do max k coverage as well and show that you have a 1 - 1 over the approximation for max coverage, k coverage.